Topic03B, Assembly Language Instructions number 1. So this is the first part of a two-part series on the various instructions that we have available for our use. So now that we've actually done a bit of system analysis and design, and we've had a bit of a think about the steps we have to take in our program, now it's a matter of simply looking through the instruction set to find out which instructions do those various steps that we have worked out that we need to do in order to solve the particular problem that we have, or in order to write that piece of code to drive that hardware in a particular way. When it comes to the HS12's instruction set, or the CPU S12's instruction set, or the Adapt9S12's instruction set, they're all the same thing. When it comes to that instruction set, we have numerous different tasks. We have over 200 different instructions performing 188 different tasks, and of course we have different addressing modes on those tasks, so we have heaps and heaps and heaps and heaps and heaps of options and possibilities when it comes to solving our problem. When it comes to using these instructions, we've got many different ways of doing it, so every little piece of code to do one particular task can in fact look completely different, because you can use different instructions to do different sorts of things. You can attack the problem in a completely different way. So when it comes to our instructions, as I said, they're split up into different categories. We have load and store instructions for getting data in and out of the processor. We have transfer and exchange instructions if we want to move data around within the processor. We have move instructions, so we can move in and out of memory. We can move bytes straight from one memory location to another without even actually having to bring them inside the CPU. Obviously they're brought temporarily inside the CPU, but they're not stored anywhere inside our registers. We can do decrement and increment commands. We've got various arithmetic commands at our disposal. We've got logical commands. We've got rotates and shifts. We've got data test commands. We've got conditional branching commands, because of course our code is not going to be purely sequential. There will be stages where our code will need to branch off and start running other chunks of code based on some sort of condition that has taken place. We have loop primitive commands, because one of the key things that we do a lot in our programming is we do iterative loops. So we have loop primitives, which are instructions designed purely to easily implement loops. We have jump and branch commands, so these are our unconditional jumping around throughout our code. We also have condition code tests, so we can test various conditions, and of course we have interrupt based commands as well, so we can control our interrupt subsystem. So the first category we really want to talk about is of course the load and store instructions. Load and store instructions of course allow us to move data in and out of the registers inside our processor, so we can use a load instruction to simply load values out of memory into the core. We can use store instructions to move them back out of the core into memory. And of course, depending on the size of the register that we're moving the data in and out of, then the operand or the data that we're operating on will in fact be dependent on the size of the register. So we're using an 8-bit register, then the data that we're moving around will be 8 bits. If it's a 16-bit register, then of course the data that we're moving will be 16 bits. So there are basically load and store instructions that can operate on our accumulators, A, B, and D, our index registers, X and Y, and of course also on our stack pointer. So they are the registers that we can use to load data in and I guess store data out of with these instructions. So when it comes to loading our data, we have the commands which has an LD in front of it for load. So LD stands for load, and then the next one or two letters actually defines the register. So we've got AA for accumulator A, AB for accumulator B, we've got D for accumulator D, so, and X and Y for index registers, and S for our stack pointer. So one thing to keep in mind here is that the A in the accumulator defines it as an 8-bit, whereas if it doesn't have an A, as like LDD, then of course it's a 16-bit load. So the accumulator D, the index registers, and the stack pointer are all 16-bit registers. They don't have an A in their name because they're 16-bit. And of course, when it comes to storing those values out of those registers, we have the store command. So the ST in the mnemonic stands for store, and of course the same the same representation or same naming convention for the registers is the same as it was with the load. So storage accumulator A is STAA, accumulator B is STAB, and so forth. So to give some examples of using these commands using various addressing modes that we talked about in the last topic, when it comes to doing an immediate addressing, we're simply loading the value that directly follows the actual instruction. So, example, if we're going to load 23 into accumulator A, then it's simply LDAA hash $23. So it loads the hexadecimal value of 23 into accumulator A. We can also do it using direct or extended addressing, depending on where the variable val lives in memory. If it lives in the lower 255 bytes, then it's direct. If it's higher than 255, then of course it's going to be extended addressing. But simply when you want to do direct or extended addressing, you simply use the variable name after the mnemonic. So in that case, it's LDAA val. If you want to use index addressing with respect to, in this case, the X register, you can simply go LDAA 0, X. So therefore, it will simply load the value out of memory that X refers to. And of course, I've given numerous other examples with accumulator B, accumulator D, and of course with the two index X and Y registers. So lots of different variations that we can use. One thing to keep in mind is that when you're loading using accumulator A and accumulator B, as I said before, you're loading an 8-bit value into that register. When you start dealing with the D, Y, and X, then in fact you're loading a 16-bit value, which means you're loading a chunk of data. In the case of immediate, you're simply loading the next 2 bytes that follow that instruction into the accumulator, or into X or Y, whatever one you're using. If you're referring to a memory location, then of course you're going to load 16 bits out of that memory, which means the most significant byte that's going to go in that accumulator will come out of that memory location that you're referring to. The LSB for that register will actually come out of the memory address that immediately follows that the most significant byte. So it simply loads 2 bytes out of memory. It's stored in a big endian notation. So we have MSB at the memory location we're referring to, and we have the LSB at the memory location directly after it. So you've got to keep that in mind when you're dealing with 8-bit or 16-bit registers, that if you load to a 16-bit register, you'll effectively end up loading 2 bytes out of memory. Okay, when it comes to storing values back, of course, you can't. When it came to with loading, you could actually use immediate addressing with loading because you could load a values that directly follow that instruction. When it comes to storing those values, you can't store to a constant, so you can't use immediate addressing when it comes to storing because you can't store onto a constant value. You've actually got to store it somewhere in some sort of memory location. So we really only have 2 addressing modes at our disposal when it comes to storing, and that is either using the direct extended sort of combination or using indexed addressing. So we've got those 2 different variations that we can use when we actually come to store our particular contents out of our registers. So we can do a few examples here. We can store simply using a variable name that we've defined somewhere in our code using a DS dissembler directive, or we can specify direct memory locations, but of course it's really not a very good thing to use magic numbers. It's always better to define them using DSs and simply use their names, because that makes it a little bit more portable when you start moving your code from one processor to another. So when it comes to storing, we simply use the mnemonic that refers to the particular register that we want to store. So it's either STAA for accumulator A, STAB for accumulator B, STD for accumulator D, STX for accumulator X, STX for index X, or STY for index register Y. And then of course you just simply specify the variable that you want to store that in. And like before, you've got to keep in your mind what the size of that register is. So if it's an 8-bit register, you're only going to end up storing it onto an 8-bit, a single memory location. If it's a 16-bit register, then you're going to end up storing it onto 2 memory locations. MSB will be in the location you specify. LSB will be in the location directly following that one. And of course, you can use it. You do it also using indexed addressing, and it will be stored in memory at a location dependent on that particular index register that you actually used. So we can use the load and store commands to get data in and out of our processor, but there are also other ways that we can do our moving our data in and out of the processor. If we temporarily want to preserve a value in a register, but we're going to need it later on, so there's no real point in going to stick it at a particular variable value because we're going to need it in like a few instruction cycles time, we can actually use the stack. So as we mentioned before, the stack is a temporary storage space in memory where we have a stack pointer that refers to the top of that stack. So we can push data onto that stack, the stack gets bigger. We can pull data off that stack, the stack gets smaller. So it's a temporary storage mechanism. So when it comes to using the stack, we can push and pull many different registers onto that stack. We can also push and pull the program counter, but that's done using an indirect different mechanism using a JSR command, but we'll come back to that later. So primarily the only registers that we use using the push and pull commands directly is by storing our 5 primary registers that we actually use for general manipulation, which is accumulator A, accumulator B, accumulator D, index register X, and index register Y. So using with those 5 registers, we can push and pull their contents onto the stack. So, like I've said before, the mnemonics are pretty self-explanatory as to what they actually do. So we've got to pull a value off the stack. It's the PUL, which stands for pull, and then it's the letter that follows it to refer to the particular register that we want to pull. So pull A would simply pull the value that the stack pointer is referring to off the stack and stick it into accumulator A. We've got pull B, pull D, pull X, and pull Y. If you want to put something on the stack, then we've got the equivalent push command. So we've got push A, push B, push D, push X, push Y, and they allow us to actually temporarily push the values onto the stack. They don't actually delete the value out of the register that we're pushing from. So in case of doing a push A, we don't actually delete the value in accumulator A. It still stays in accumulator A, but we put a copy of that value onto the stack. And then later on, we can do something with accumulator A. We can trash that value in accumulator A, override it, do some other processing with another data value, and then later on, when we need that value back in accumulator A, we can simply pull that value back off the stack using a pull A. So it's a good way of actually temporarily saving values that we might need later on. So I've given you here a very simple example of using the push command. So we simply load accumulator A with the decimal value 32, and then we simply push that value onto the stack. Okay, so therefore what happens when we do a push A? The stack pointer is decremented, so stack pointer equals stack pointer -1, so it points to the memory location slightly lower than where we currently are, and then we simply store that value of A at the memory location that the stack pointer refers to. So the MSP notation that I've mentioned here, this is a notation that I use throughout this lecture set, but basically it means that our memory, which referred to in this case as M, is a continuous array of 8-bit values. So I use that notation to define that MSP is, of course, the memory location that SP refers to. So it's like, I guess, the index value SP of an array called M that represents our entire memory map. Okay, so we've looked at the ways of getting data in and out or temporarily putting them on a stack. There are other commands that you might want to do. So we might actually load a value into a particular register, do something with it in that register, and then realize, hey, we don't have the facilities that we require in this register, because some registers have special capabilities, others don't. So we might want to do, say, a multiplication. The value we want to multiply with is in the wrong register, so we need to get it in the right register. So we have these series of commands that allow us to transfer data inside the microprocessor. So we can transfer data from one register to another. There are a series of inherent commands that allow us to swap or transfer values from accumulator A to accumulator B. So we have a TAB command, which simply allows us to transfer A to B. We have the opposite, which allows us to transfer B to A, called TBA. So the T stands for transfer, and of course the 2 letters after that refer to the source register and the destination register. We can also simply use the TFR command and simply specify which registers we actually want to move the values to. So we can go TFR source register, destination register, and I've given some examples here of TFR SX, so we can transfer the stack pointer to X and the stack pointer to Y and so forth. So we can transfer the various values from one register to another simply using TFR. So that's primarily the major mnemonic that you need to remember when you're doing transfer is TFR, because you can simply go TFR AB and the assembler will actually automatically translate that to a TAB for you. When it comes to exchanging, so we want to actually swap the 2 values in a register, so we might want to in fact move one register value to another and just swap them around. We can use the exchange command. So using the exchange command, we can transfer two different registers around. They don't have to be the same size, and I'll show you what happens when we start transferring or exchanging registers that are of different size. So in the simple case where we have a transfer from one 8-bit to another 8-bit, of course the 8-bit value just simply moves across, no problems. Same thing with the 16-bit value. If we're transferring from one 16-bit register to another, the 16-bit value just simply moves and there's no problem. Okay, so if the registers are the same size, it's pretty straightforward. But what happens when these registers are different sizes? What happens when we try and move, say, a 16-bit register into an 8-bit register? You know, it's like trying to fit a really big item into a very small box. It's not going to fit. Okay, we're going to lose something during this transfer. So what are we going to lose? Well, when we transfer it, we simply transfer the least significant byte. So the LSB moves and the MSB doesn't move at all. Okay, so effectively if we had a number in that register that was greater than 255, then of course we've lost the significant portion of that number. So before you do a transfer like this, you probably want to check to make sure that number is not greater than 255, otherwise, you know, you can't do it. So generally you'd only use a transfer like this in a situation where you knew the value in that 16-bit register was going to be less than 255. Okay, if it's not going to be less than 255, then you just can't do it. You're going to lose the number's just going to be completely different to what it originally should have been. Okay, in a situation where we transfer from an 8-bit to a 16-bit, so when you move from an 8-bit to a 16-bit, the 8-bit value simply transfers into the lower 8 bits of the 16-bit register, and the most significant byte of that 16-bit register is in fact zeroed. So we basically preserve the magnitude of that 8-bit number by simply moving it into the lower 8-bit portions of that register, and therefore the magnitude or the value of that number remains intact. The MSB is automatically zeroed, so we don't end up with any sort of corruption of that number. So what happens in a situation where we do an exchange, where we move, want to exchange a 16-bit and 8-bit register? Well, it's effectively a combination of the two things we've just done there. So when we do that, we simply have the least significant byte of the 16-bit register moved into the 8-bit register, the 8-bit register value moved into this lower portion of the 16-bit register, and the MSB was actually zeroed. So effectively, as long as the value in the 16-bit register is less than or equal to 255, we've had an exchange that hasn't corrupted any of our numbers. So yet again, like I said before, you need to check to ensure that when you do an exchange or a transfer from a 16-bit register, you ensure that the value in that 16-bit register is less than or equal to 255. Otherwise, it's just going to cause a random sort of value being transferred for you, or an incorrect value at least. Okay, so another really good instruction that people seem to overlook is the move instructions. People still tend to want to load values into registers and then store those values back to some memory location, but you don't have to do that. You can simply, using a move command, you can simply move data from one memory location straight to another, or you can move an immediate value straight to a memory location without having to go through the two-step process of a load and a store. So it makes your code look a lot nicer if you're simply using moves instead of a load into a register and then a store back. The other advantage is, if you're loading into a register and storing back to a register, then you're utilizing a register that you don't necessarily have to use. So if you're doing something quite complex where you've got all your registers loaded up, you actually can just do a move without actually having to free up a register by doing a push and then loading the value into that register and then storing it back and then pulling the value back from the stack back into that register. So it makes it a little bit easier if you're just simply using moves, because using a move, it uses a temporary unnamed register inside the processor, simply loads it into that and then stores it back to some memory location. So it leaves our register set, so to speak, alone. So it's a really good way of moving data around. So when it comes to using the move command, our source that we want to move can be a constant or it can be a memory location. Okay. However, the destination always has to be a memory location. You can't, as I said before, you can't store to a constant. So the source can be a constant or a memory location. The destination always has to be a memory location. But the memory locations that are referred to in the source or the destination, they can either be defined using direct or extended addressing, or even using indexed addressing. So we've got many different possibilities there when it comes to using these commands. So when it comes to using the move command, the first example here, I've got a move B. So one thing you've got to realize with the move commands is the move B, the B defines byte, the W defines word. So move B, this is examples using the move B command, which is moving bytes around, so only 8-bit values move around. So the first example here, we've got move B 23 to data. So what happens is we actually move the decimal value 23, which obviously would be sitting in the instruction queue because it's an immediate value. It's directly following this instruction, so we simply grab that value out of the instruction queue and we simply move it to the memory location that data refers to. So 23 simply moves into the memory location that data refers to. So yet again, I've used that notation of M, which is defines our memory of a contiguous array of elements, of 8-bit elements, and then data is, I guess, the element in that array where the variable data is, the label for that variable, label data, is actually referring to the particular location inside that array. So we can also do move from a memory location to another memory location. So we can do a move B from port A. So port A is a named memory location, and we can move that onto another named memory location, another variable memory location called data. So we can move from one memory location to another. Another example where we do a move B of a hexadecimal value FF onto port A. So simply we move that immediate value that will be in the instruction queue straight onto port A. Okay, and we've got another example here where we move the decimal value 23 into a memory location where we've actually used its address value. We haven't given it, we don't have a label referring to that address, we've actually used its direct address value. And as I said before, we really want to try and refrain from using actual address numbers, but I've just given it here as an example. If you really desperately have to, then here is a way of actually doing it. So simply by doing a move B, we can move the decimal value 23 into the memory location 1234. So that is actually the index, hexadecimal index 1234 of our array, or our contiguous memory array. Okay, so like I said before, we have move B for moving bytes, we have move W for moving words. So when it comes to moving a word, so in this case we want to move the immediate value 1423 into a named memory location data. Obviously this memory location data would have to be different to the one on the previous slides because we're moving 8-bit values into that location, so therefore that sort of defined that data label was referring to a single 8-bit location, whereas in this case we're going to need 2 bytes to hold these results of these moves because we're moving words. Words are 16 bits, so therefore the destination location in our memory would at least have to be 2 bytes in size or 1 word in size, which are effectively the same thing. So when it comes to moving words around, we simply specify the move word, we specify the source, which in this case is the constant 1423 in hexadecimal format, and we want to dump that into the memory location referred to by the name data. So the data is effectively a label to a particular memory location where we want to store these values. So when we do a move word, effectively what happens is it splits it up into 2 bytes and stores those 2 bytes in consecutive memory locations. So the 14 is the most significant byte. 14 is stored into the memory location referred to by data itself, and the value of 23 hexadecimal is stored in the memory location that directly follows. So in this case, data plus 1. So it's index of data plus 1 in our memory. So it's the memory location directly under where the 14 was stored. So if you looked in the memory, you'd see the hexadecimal 14, and then in the memory location directly following that, you'd see the hexadecimal value of 23. And of course, if we want to do a move word with a memory location to another memory location, then you need to be very much aware that when you do a move word, you're moving 16 bits. So if I do a move word port A to data, then effectively what's happened is it's going to move the 8-bit value that port A refers to and store that into the memory location that data refers to, and then it's simply going to go to the next memory location under port A, which in this case is port B, because port B is directly under port A in the memory map. So it's going to grab the value from port A and simply store that value into the memory location that directly follows where it stored the value for port A. So effectively we have port A being copied from value in port A being copied from port A and being stored into, I guess, the variable that data refers to. And then we have the value in port B, which is directly after port A, being copied across to be stored in the memory location directly after where we stored the value for port A, so to speak. So we have a 16-bit value moving from one memory location to another memory location. And that's something you've got to be very careful about when you're using either load, stores, exchanges, or moves. Is you've got to be very careful about the size that you're moving. Because if you're in the first example here where we're moving to data, if your data only predefines 1 byte in size, and you simply go and store a 16-bit value in that data, you're going to end up deleting whatever variable immediately followed that data variable. So you've got to be very careful about when you're moving stuff around. There's no error checking in the assembly domain, so you need to be very careful about how you use instructions and be very careful that you don't corrupt your data. We also have a series of increment and decrement instructions, because one of the very common things that we like to do inside programming is we simply like to increment variables, or we like to decrement variables, simply have a series of counters sitting inside our code somewhere. So we can actually do increment or decrement on the primary set of registers, so we can do it on accumulator A, accumulator B. Okay, we can do it on the index registers, we can do it on a stack pointer, and of course we can do it on memory directly. So we don't even have to load the value into memory. We can simply go inc and specify some data or some variable name, and simply it will increment that variable name or decrement that variable name for us. So we have INC, which represents increment, and then of course the same notation as before. We have the letter that follows, which defines which particular register that we're going to increment, or in the case of memory, we just simply have inc and then we specify the memory. So like before, we have the same notation as before. If it's INC, it refers to 8-bit. If it's IN, it refers to 16-bit sort of memory size. So where we have increment, we also have the decrement. So we have dec A, dec B, dex, dec Y, des, and dec memory as well. Okay, I've got an example here of using an increment instruction. So in this example here, I'm using the serial subsystem so that I can actually echo some data back to the terminal screen. So first thing I've done inside here is I've actually initialized the serial device. So I used an init SCI library command to initialize the serial subsystem. I've then gone and loaded accumulator B with the number 2. So I've immediately loaded the number 2, which in this case is in decimal format, into accumulator B. I've then used an inc command, in this case inc B. It's an inherit command. It has no operands because it's got everything it needs. Simply increment the contents of accumulator B. So what it will do is simply increment the 2 that's currently in accumulator B to be the value of 3. So now we have 3 in accumulator B, and then I use a subroutine called out2hex, which is useful for printing hexadecimal values to the screen. So out2hex prints whatever the contents are of accumulator B to the screen. So when I do a JSR out to hex, whatever is in accumulator B, which in this case is the value 3, will be displayed on the screen. So on the screen you'll get the character 0 followed by the character 3. So you'll get the value of 3 being printed onto the screen. And then we hit our branch always loop, which causes us to spin on the spot. I then have some subsequent setup requirements for the serial subsystem. So I've actually defined a label to define the base address of the serial subsystem that we're using. In this case it's the auxiliary serial subsystem, so it's set the base up to be 00D0, and then simply included the serial library code as well, so therefore when I assemble it, it knows everything it requires. I've got another example here using an increment command, but this time I'm incrementing a memory location. So somewhere inside my code, down the bottom I've shown it here, but generally it'd be in the RAM section because it's a variable. So inside the RAM section I've actually defined a label called counter, which refers to a single byte of memory. Okay, so then what I do is I simply initialize a serial device like I did before. I move the value of 2 into the actual memory location that the counter refers to, and then I simply increment that memory location that counter refers to, so therefore I simply have the value of 3 inside that memory location that counter refers to. And then what I do is I then simply load the value that counter refers to into accumulator B. Okay, because I want to be able to print it out without to hex, it has to be in accumulator B. So I load it into accumulator B, and then I JSR out to hex, so therefore I get the value of 03 printed onto the screen. So you can see both these examples do exactly the same thing, except one was incrementing a register, this one is incrementing a memory location called counter. We also have a series of commands that allow us to clear and set registers. So we can actually clear an entire register, we can clear bits in a register, we can set bits in a register. We've got two different types of resolution here. We can do register-wide clear, or we can do bitwise setting and clearing. The commands that allow us to clear a entire register are the clear commands. So we've got CLRA, CLRB, and we've got also CLR, just simply clear a memory location of some kind. So we've got commands that allow us to clear memory locations. And there's a few more of these clear commands, but I've just illustrated a few of them here to give you a basic idea of what we have available. But if you look at the mnemonic set, you'll probably find there's a few more that are easy that you can use easier. Instead of having to, I guess, load a 0 into a particular register, you can simply clear that register. Because of course the loading takes a few more cycles to do, whereas a clear is simply a single cycle to clear it. So as I said before, we have the ability to set or clear particular bit values inside a register. So this is very useful when we're dealing with subsystems where we have particular bits that control particular aspects of that subsystem. So we may in fact need to just set one particular bit but leave every other bit alone. So we might just want to only change one bit value but not affect the other bits. So we want to leave the other bits alone and untouched. So we actually have bit set and bit clear commands. The thing that people really get confused about with these commands is they think that a bit set and a bit clear command works a bit like a move command, but it's not. It's nothing like a move command. What we have with these commands is we have the command either bit clear, so BCLR, or bit set, BSet. So we have these two commands, and those commands define the action that they actually do. Then we have an operand, which is some location, some register or some memory location that we actually want to modify. And then we have a mask that allows us to define at a bit-wide resolution which actual bit we want to modify. Okay, so it's the mask that defines the bits that we want to modify. It is the command, in this case bit clear or bit set, that defines the action that we want to do with those bits. Okay, so the mask defines the bits we want to change. The command defines how we're going to change them. Okay, so it's the command that defines how the bits change. It's very clear. You've got to keep that very clear in your mind when using bit sets. Bit clear. They're a great command to use. They make your life a hell of a lot easier, but you've got to know how to use them properly. So to try and illustrate that a bit further, I've actually got an example here. So we're using a memory location called port A. Okay, it's a general purpose I/O port. It's quite a useful port. You'll be using it a lot, or if not port A, one of its subsequent general purpose I/O ports. But general purpose I/O ports are registers we use a lot. And we like to be able to do bit resolution changing of those ports because we want to change particular I/O lines that come in and out of the processor. So first of all, we load the port with a starting value. In this case, it's 10101010. Okay, so every alternate bit is a 0 or a 1. Okay, that's how we start port A with that value. So when we run a bit set command, with the bit set we have the mask, which basically says we want to modify the top nibble. So we want to modify the top 4 bits, in this case the top 4, but we don't want to touch the bottom 4. Okay, so the mask defines the top 4 we want to change. So the 11111 in the mask says we want to change the top nibble, but we want to leave the bottom nibble well alone. And then you look and think, well, how do we want to change that top nibble? Well, it's a bit set command. So we want to change that top nibble by setting all those bits in the top nibble. And that's when it takes place. So the top nibble is now all 1s. The bottom nibble is unchanged. It's its previous value. So that's one thing to keep in mind, is that when you do a bit set, it's not going to zero the bottom 4 bits. It's going to leave them unchanged, but it will set the top 4 bits. So whenever you do a bit set, whatever you've got in the mask, that will effectively set those particular bits. So if your register was originally 0 and you did a bit set, then yes, the resulting register will look a bit like you've done a move, but it's not. All it's done is simply set those bits that you defined in the mask. So the result is 11111010. Okay. When it comes to doing the bit clear, same thing takes place here. The bit clear, the mask specifies 10101010. So effectively it's specified every alternate bit. So we've got bit 1, bit 3, bit 5, and bit 7 being selected. Okay, so we've selected those bits. What do we want to do with those bits? We want to clear those bits. So we're using the bit clear command, and therefore those bits that we've selected will in fact be cleared. And that's what happens. Those bits are cleared. The other bits that we didn't select in that mask remain unchanged. That's something you've got to keep very clear in your mind. Okay, so another operation that we like to do inside the processor, we like to move data around inside the register. So we actually like to shift it left or shift it right by a single bit at a time. The beauty of shifting data left or right is that we can, if we're connected to a particular I/O device, we can strobe a particular line at a particular time simply by using rotates. We can change the magnitude of a number by 2 simply by shifting it left or right. We can shift it left and it multiplies it by 2. We can shift it right, we can divide it by 2. So depending on whether we move it left or right, we can in fact do very simple multiplication and division by 2. We can either do arithmetic shifting or we can do logical shifting. The two do differ slightly, and I'll go through some examples to show how the two commands differ. Basically, we can shift left or right with these shifting commands, and we can do this using accumulator A, accumulator B, and of course accumulator D. So these are the 3 registers we can use with our arithmetic shifts. And of course, we can also do it on memory locations as well, so we can shift memory locations. Okay, so we can either do arithmetic shifting or logical shifting. So like previously, the name is sort of gives away what it does. So arithmetic shifting, it's A, S for arithmetic shift, and then it's the letter depending whether we're going left. So L for left, R for right. Okay, so the name pretty much gives it away as to what it does. And then of course the letter on the end defines whether we're doing it on accumulator A, accumulator B, or accumulator D. With logical shifting, it's LS for logical shift, and then it's L for left or R for right, and then the register that we're going to be doing the operation on. So it's either A, B, or D. So the name's actually fairly logical in how they sort of work. Okay, so to give you an example of how the shift and rotate instructions work, so when it comes to logical shifts left or arithmetic shifts left, they both work in primarily the same way. So when you're shifting it left, we basically, in this example here, we started with the least significant bit being set to 1. So when you do a logical shift left, the whole register moves along by 1 bit. We zero pad the LSB, so put insert a 0 on the least significant bit, and we move the whole register along by 1 bit. The most significant bit falls off the end and goes into the carry bit of the condition code register. So effectively we've got like a 9-bit shifting register. So the 9th bit is the carry bit inside the condition code register. So if we do another shift, simply move it along by 1, we zero pad the least significant byte. The most significant byte has gone into the condition code register, the carry bit, but then the bit that was in the carry bit of the condition code register has actually been moved out and it's gone, it's lost. Okay, so it's gone, we don't have it, so after 9 shifts, we've actually lost all the contents of that register. Okay, so we can keep moving it, so we move it along left by 1 more, zero pad the least significant bit, most significant bit moves into the register, and we simply lose that value that's in the condition code register. And we can skip a few steps, and we've done a few more logical or arithmetic shift lefts, and now we've got the 1 in the most significant bit location. If we do one more logical shift left, Then that value moves into the condition code register, and we have it in the condition code register. And of course, we do one more logical shift left, we lose it, and therefore the entire register is now 0, it is empty. So after 9 logical or arithmetic shift lefts, our register will be zeroed, it will be emptied, we've lost all our data. But the beauty of it is that each time we've shifted it, it's shifted through that condition code register. So there are a lot of conditional commands that actually work on the condition code register, and in particular the carry bit in the condition code register. So you could do like shifts, and you could like test that carry bit. The carry bit set, we do something. So you could actually use it to shift that value through the carry bit in the condition code register, actually see each little bit allocation and maybe do something in your code with that particular bit, depending on whether the condition code, the carry bit in the condition code register is set or not. So there are useful ways of actually moving data through the carry bit. Okay, when it comes to moving things right, this is where things start to differ with our arithmetic and logical shifts. So generally, if you're using signed numbers, or if you know that the value you're dealing with is a logical represented number, or whether it's an arithmetic number, then it pays to use the actual correct shifting mechanism. So if the number is simply off a general purpose IO port, where it's just simply digital values that you've read from the outside world, then you might just want to do logical shifts. If the number you read, if the value you've read is actually a number, and you know it can be signed, you know it could be a positive or negative number, then of course by all means make sure you use arithmetic shifts. Okay, because when it comes to shifting right, you can really screw up a number if it's signed. So if you've got a signed number, let's say negative, and you start doing logical shift rights on it, all of a sudden you've lost that value. That value will be corrupted. However, if you use arithmetic shifting on it, the value will change, but its sign will remain intact. Because what happens when you have a negative number, so if you have a 2's complement representation of a negative number, the most significant bit is always set to 1. Okay, so if you do a logical shift right of a negative number, what logical shifting does is it zero pads the front. So you can see in the slide here we have a 0 sitting above that bit ready to slip in. Okay, so if you do a logical shift right of a negative number, effectively a 0 will go on the MSB, the negative number will instantly change to a positive number because the MSB is no longer 1, and the actual magnitude of the number will be all screwed up as well, so it won't even be the right magnitude. So you lose a sign as well as you lose the value, so the number will be corrupted. However, with arithmetic shifting, as you can see, there's a 1 here ready to go in, and it can be a 0 or it can be a 1, but basically whatever the current value is in the most significant bit is the value that it will substitute in when you do a arithmetic shift right. So when I do an arithmetic shift right, if the most significant bit was already 1, it will pad it with a 1. If the most significant bit was a 0, it will pad it with a 0, which means that the sign of the number will remain unchanged, and the magnitude of the number will simply divide by 2 each time we move it right by 1. Okay, so the arithmetic shifting will in fact preserve the sign of the number, and it will ensure that we're simply doing divide by 2. So whether that number is positive or negative, when you do arithmetic shifting, it simply divides by 2 each time, so it ensures that numbers are not corrupted. So if you know you've got a signed number, then by all means make sure you use arithmetic shifting. If you're not sure, arithmetic shifting is the safest bet, unless of course you know it's a logical number that you've read out of a register and you just need to like rotate it or move it around, then of course use logical shift rights. So depending on the application, make sure you use the right command. So to give you an example of how this works, so we simply move it, shift it right, and in both cases of the logical and arithmetic shift, the least significant bit slips off the end and goes to the condition code register. Okay, and then what happens is we pad the front with those respective digits. So in logical shift it's always a 0, arithmetic shift it's either a 1 or a 0 depending on the most significant bit value, previous most significant bit value. So you can see we've gone now, we've arithmetically shifted it. The number on the arithmetic shift right is still the right value, it's still a negative number, but now it's half of its original value. Same thing with logical shift, it's half of its original value, but that's only lucky because it was already positive. So what's happening each time we're doing these shifts, we're shifting right, we're simply taking the least significant bit that falls off the end, putting it in the condition code register, and padding the MSBs with the respective values depending on whether it's logical or arithmetic shift. So we'll do that again. The LSB slips off the end, goes to the condition code register, and then of course we insert the respective values in the MSB. So because the arithmetic value was negative, we're simply putting the 1 back in there in its place. If it was a positive value, so if the original MSB was 0, then of course we'd be padding it with zeros each time. Okay, so, but of course, as I said before, when you're doing shifts, after 9 shifts, you've simply, shifted that value off the register, and because it's padding it with 1s or zeros, what you're going to end up in the end is you're either going to end up with 0 or you're going to end up with -1. Okay, so if you're doing a logical shift, eventually after 9 logical shifts, you simply got 0 on the register because you've been 0 padding the front. When you're doing arithmetic shifts, after 9 arithmetic shift rights, you're either going to end up with 0 if it was a positive number, or you'll end up with -1 if it was a negative number. So depending on which the original value in that register, when you're doing arithmetic shift right, you'll either end up with 0 or 1. So basically you're going to lose that original value. So in situations where you want to say rotate, or you want to shift the value through the condition code register, but you want it to be back to its original value after 9 shifts, then you might want to use a rotate. So rotate will effectively rotate your register through the condition code register and back into itself. So effectively you've got a 9-bit rotating register. So the LSB slips off the end, goes through the condition code register and back onto the register after two shifts left, after 2 rotates left or right. So to show you this example running, so I've got both the rotate right and rotate left examples happening at the same time. So you can see that when you rotate right, simply move the condition code register value on, and we simply move the LSB back into the condition code register. Same thing, we rotate left, the condition code register value goes into the LSB, and the most significant bit goes into the condition code register. Okay, so it simply rotates through this 9-bit register. You can do that again. See the condition code register into the actual register, and the LSB into the condition code. Same thing, rotate left, condition code register into the least significant bit, most significant bit into the condition code register. So you can see it's sort of rotating through that 9-bit register, where the 9th bit is in fact the carry bit in the condition code register. So, yet again, if you should require some assistance at any time, please do not hesitate to ask the demonstrator. Post a question on the forum, email me the convener, okay, or make an appointment to see me. Either way, make sure your questions are answered. Grab me after the lecture, grab me after the tutorial, come hound me at my office, whatever. Just ensure that your questions get answered, okay?